Okay, let's start. So you're handing in your homework? While you're handing in your homework. So this summer I'm teaching 2 different Calc 2 courses if you're interested. Some of you are here because you're engineers and you need 265. If that's you, then you could take either one of these, 266 or 271. 266 is already filled up, but if you're my student in this class, I will write you an override if you want to keep going, okay? That's only engineering majors who are here because you need 265, okay? You could go back, you could do 266, all right, you'd be fine. The rest of you who need 270, you would probably also need 271, okay? So that one's still open. All right, the 266 is an A session. That's mostly in June, and then the 271 is mostly in July. It's the B session, mostly in July. Okay, and there you can see all the information. So if this is of interest to you, you can write down the SLNs over there: 43158, 41239.
We offer this over next fall.
I'm not teaching Calc 2 in the fall. I'm only teaching Calc 2 in the summer.
Okay. What's the big difference between
Not a lot. 271 is 4 hours. 266 is 3 hours. 266 is the requirement for engineers. 271 will take care of any Calc 2 requirements. So if you need 271, you can't take 266. But if you need 266, 271 is okay. So 271, the 270 series will take care of any calculus requirement that you need. Okay? But if you're an engineering major, you have the option to do either one. Okay, so quick, write that down if you're interested. Or you can send me an email if you have more questions about that. But yeah, these are in the summer. Last chance. Any questions? Okay. Oh, and then Thursday's homework is posted. Well, it will be posted at 10 a.m. That will appear at 10 a.m. It's to do the section that I posted and told you we do Thursday, and then the quiz for Thursday will be posted. Sample quiz. And then our next exam is scheduled for next Wednesday. So, yes, that was always the plan. So, here we are, a week away from our next exam. So, if the first exam didn't go as well as you hoped, the remedy is start studying earlier. Start studying earlier, and then those last couple days before the exam is your chance to get into our office and ask us questions and get your questions answered. So let me just remind you, there's the office hours and tutoring. There are 6 different people that are available to you who can help you with this course. I need to adjust. I think her hours are wrong, but I'll adjust that. But find these people, and the hours are spread out over the week. Okay? So I'm available in my office. Both your TAs are available. And then there's these other 3. And you can just go knock on their door. They're extremely nice and welcoming. And they know what we're doing in this course. They can help you with it. Okay? So start studying early. Get the help you need. That's my advice if you want to try to improve your performance. Okay. So your last homework problem was it a falling ball? Something was falling. And so you start with a rate of change. You know that it tells you that the rate of change is what? Negative 32t? Is that right? So if you were to sketch that rate of change graph, so it's negative because height is positive up from the ground, right? So the direction of positive height is up. So if the ball is falling, going down, then that rate of change is negative because that height is decreasing. So this is your initial sketch of the rate of change. And so we want to develop a step function out of this so that we can develop an accumulation function. And if the rate is continually changing, that's problematic for us, right? Because we want to use the math of constant rate of change, which is easy. Okay, so we're going to form a step function, and I think it was a little bit open-ended in that, how you were going to do that. So in this, the way that I've set it up, I'm using the left sides of intervals that are half a second long. So I used half a second, and I used the left side of each interval to determine what that pretend constant rate would be. So looking here. Okay, so looking here in the first half second, what is the rate at the left side of that interval? In other words, what's the rate at 0 seconds? 0. So I'm going to have, so then what's the pretend rate at 0.3 seconds? 0. What's the pretend rate at 0.4 seconds?
0.
0, okay? The real rate is shown by the pink graph. Okay? So then the first constant rate of change is 0 in the first half second. All right? And then the next, if that rate is decreasing 32 every second, then the next half second, the starting rate of change is negative 16. And so that's what I'm going to pretend the rate is for that whole half second, a constant of negative 16. And so likewise, negative 32, negative 48, negative 64, and negative 80. Yes, please.
Wouldn't we use the other side? Instead of doing like from 0 to 0.5 at equals 0, wouldn't it be I thought we used the right side. That's not
You can choose.
Okay.
We're making up a pretend function, and so you can choose the right, unless it specifies in the problem. If you just have a rate change function and you're going through this process, you can choose. You can choose the left side. You can choose the right side. You can choose the middle. Okay, so that's called the mid approach, where you would choose the rate of change in the middle of the interval. So all of them work because it's just going to be an approximate rate of change in the end. Okay, what doesn't work is to come up here and say, okay, I want my first constant rate to be 200, and then I want my next constant rate to be 400, and then so it's not pretending to be what we have. The whole point is any systematic way of pretending to be the given rate works. So I chose left, and I chose every half second. Okay, so the whole reason we make this pretend rate of change out of constant rate of change is so we can use the math of constant rate of change, which says that any change in height now will be that constant rate times, in this case, the change in time. So if you go 0 feet per second for half a second, what's the change in height going to be? No change, right? And if you go negative 16 feet per second for half a second, what will your total change be? You'll go down by 8, right? You're going to go down by 8. Makes sense. And this is we're just doing k delta x. The rate of change times the speed times the number of seconds. Okay, and then for another half second at negative 32. Okay, so this is how much the actual height is changing according to our pretend rate function based on constant rates. So down 24, down 32, and then down 40. So again, we've got our side-by-side graphs. We've got the rate of change on the left, and we use the constant rates from our pretend function to build the accumulation. What's the accumulation in this case? It's the accumulation of height of the ball. Okay, so I've tracked the changes. Now I can come up with a table that kind of shows this height function. So if it starts at 120, in the first half second it drops by 0, then what's my height after half a second? Still 120. So again, remember that's not realistic. but it's based on our pretend function where it's just going to hover for a half second before it actually takes on a speed. All right, then in the next half second, if it goes down 8, then the new height is 8 less than what it was before. And so then we keep decreasing by these delta h's that we calculated using k delta x. Okay, likewise, we could write using these step function. So this is a kind of a table version of this accumulation function. What is the journey we're on? You have the rate of change function. You want to build an accumulation function. So this is a table version of that function. We also know we can write out these linear pieces using our slope intercept or slope point slope form and make a piecewise function that not only gives us the values of h at the breakpoints, but then at everything in between. So this is a continuous function made up of these pieces, and we've done lots of that. So these are two different representations of the same function. This is kind of a table, kind of a chunky version, like point every half second, what's the height? But then this gives that a function for the height at any time x, okay, based on a piecewise linear function that we've been doing. And we got the rate times x minus starting x value plus starting y value. Then the rate, x minus starting x value, starting y value. This should be very, very familiar. Okay, what if we used a lot more steps? If I used 20 steps or 100 steps? What would be the result of that? What would be the consequences of that? What's that? More precise or less precise? Or more accurate, I should say more accurate or less accurate? It's going to be more accurate. Why? Because if you use more steps, imagine lots of teeny little steps. Those steps will do a lot better job of mimicking the actual rate function. These big, long steps, they get away, because they're so long, they deviate a lot more away from the actual rate function than little teeny steps would, right? And we'll see that later in class. We'll see a good example of that. Okay? But it's a lot more work. So if there are 100 steps, then how many lines in our step function? 100. How many lines in our piecewise linear accumulation function? 100. So there's a trade-off. If you want something that's better, it takes more work, a lot more work. Okay, but so then here's where graphing calculator comes in, because if we can set this up for graphing calculator to do it automatically, it doesn't matter if it's 5 steps or 1,000 steps. Graphing calculator can do it very, very quickly. And so we can choose 1,000 steps and get something very accurate. Okay, so that's why we're working so hard with this graphing calculator, because it can do a very powerful thing for us. And it will make our results much more accurate at low cost. Well, we've been paying the price so far to learn it, to learn graphing calculator. Once we learn it, we can apply it, and then we can easily get very accurate results. Unlike this, which is very, chunky and imprecise. Okay, so we talked about that. It would be a lot smoother and more accurate, right, if we use more steps. Okay, so today we're going to define step. Instead of doing it in one line, separate line for every step, we're going to define it in one rule. Not piecewise, one rule. So step x equals, and we're going to have a rule, a formula that will give us the whole step function, every step. Okay, that's what we'll do today. And then soon, Thursday, we're going to define this as one rule as well, the accumulation function. This is our goal. Okay, so if we want this to be accurate, that's going to mean lots of lines in the accumulation function. We don't want that. So we want just this accumulation function to be one line, one formula. Okay, so that if we make the number of steps large or make the delta x small, we get something really accurate. But we've got it in one line, one formula. So that's where we're going. So today we'll do step x in one line instead of one line, instead of one rule for every step. And then Thursday we'll likewise do the accumulation function in one formula, one rule. Okay. So all right, so I've got this this red graph here, R for rate. It's a rate function. So based on everything we've been working on, so I'm showing you an animation here. I'm showing you x, that's our independent variable, whatever that is, whether that's time or what, taxable income or something else, you know, whatever that independent variable is. Number of gallons, right? So it could be, it's whatever that independent variable is, I'm showing it increasing continuously through intervals. Right now I'm showing intervals of 1.78. Delta x is 1.78. And so we think about that independent quantity increasing. And as it increases through the intervals, the hand is pointing out what? The x value at the left side of the current interval. So whatever the current interval that x is in, the pointer is showing the left side. So based on what all we've been doing recently in the course, why do we need this? So we're interested in, given a value of x, the blue, why do we need that, what we're going to call x left, x sub L, the left side of the, yeah.
Isn't that the x initial? We're trying to figure out.
X initial?
Yeah.
Okay.
When you like x, like the final x minus initial.
Okay. Yep. So in a given interval, it's the initial value of x. Why are we interested in it? Why do we need it? All right. Maybe have a conversation. So try to relate this to what we're doing recently. It should greatly relate to what we're doing recently. So talk to the person next to you. Why do we need this value that the pointer is pointing at? Given a current value of x, the blue one, why do we need that left x value of the current interval? Go. All right, let me give you some more to think about as you answer that question. Ready? It should have had to do something with this now, so I've added to the animation. Keep talking. Why do we need that left x value? Why do we need that x value at the left end of the current interval? Keep talking. Okay, where is Joseph fallen? Where's Joseph fallen? Oh, there you are, the back. What'd you say about this? Why do we need that left x value of the current, what we call the current interval, where the actual value of x is? What's that?
Where you start the next step.
Okay, has to do with the step for that, the next step. Okay. Anything else? All right. Yeah.
It's the
Rob.
pretend rate you're going to use for that entire interval.
Okay.
If you're doing left side.
All right. So the pretend rate for that entire interval, is that x value the pretend rate for the entire interval?
No, the pointer, the y value of where the pointer is.
Okay. So that x value, we're going to use that x value to get the y value that will be what? The constant rate for that whole interval. Do you see that? That's what's happening. So that's exactly what we've been talking about, right? So if I come along here and all right, so I'm going to pause it right there. Come on. There, that's good. Okay, so I'm going to pause it right there. So what is, right now, what's the pretend rate at the current value of x? So the current value of x is, I think it's in the next line here. The current value, there's the current value of x, 6.71. So, what's the pretend rate? How would you find the pretend rate at 6.71? What's the pretend rate at 6.71?
The y-axis is the rate of change.
This is a rate of change function. The red one is the rate of change function. We're making the pretend rate function. So what's the pretend rate at 6.71? What's g?
That's how you set it off. But is it really R?
It's r.
Okay.
Yeah. Sorry, this is so. Let's just make it r. Thanks. There we go. Yeah, so it's r of x. So, one more time, what's the pretend rate at x equals 6.74? What's the pretend rate? Matt?
It's the value of the point before them.
The point, which point?
The point highlighted by the person.
So, it'd be this x value. That's the pretend rate.
No, at the R of that point.
R, he wants r of this.
Yes.
R of this would be the pretend rate at our current x value of 6.71. What's the actual rate at the current x value? What's the true rate? R of 6.71. R of 6.71. But if we want the pretend rate, we're building this pretend function, we need R of this. So that's why we need that value, because what is this? What is this? Okay, so I want you to figure it out. A, so I'm going to tell you, this is something new here. We use A to mean where we're going to start accumulating. A is where we're going to start our accumulation. So accumulation doesn't have to start at x equals 0. We can specify where it starts. So here A is 0.5. We're going to start accumulating at 0.5. We're using intervals of 1.78, So I want you to find what is, any way you can, finding the exact value of that thing we need to plug in to R to get the pretend rate for this x value. So we call that XL. So any way you can, figure out what XL is. Go. What is XL for the current value of x? This x value, where the pointer is pointing, what we just talked about. This x value that we need in order to get this pretend rate. Find out what it is. Figure it out. What is it?
Right, and that's it.
Yeah.
So it turns out like, yeah.
All right, where's Jordan Pacello? Where's Jordan? Any luck? Nice and loud, sorry. XL, that's the point and focus. This is what we need in order to get this pretend rate here, right? That's what we need to get the pretend rate. So what did you be able to figure out what that value is? Okay, didn't make progress, or started a little bit. Were you going to answer?
Yeah, I was going to say that R of 5.84.
And how'd you get that?
I just added, so there was 1, 2, 3 intervals of 1.78, which is plus 0.5, because that's your starting point.
Yeah, so we're going to start at 0.5, and how many full intervals do we have? 1, 2, 3, so 0.5 plus 3, 1.78. So either you should have figured that out, or you should be able to see that pretty easily now. It's your starting point, plus you're going to add 3 intervals of delta x, and that's going to take you to that. And what value did you say it was?
5.84.
So what's our pretend rate at 6.71? What's the pretend rate? How would you express the pretend rate at 6.71? R of 5.84. What about the pretend rate at x equals 7? What's the pretend rate at x equals 7? R of 5.84. What's the pretend rate at x equals 6? What's the pretend rate at x equals 5?
It's like 4.1.
Whatever this is.
R 4.16.
Okay, but how would you find it out exactly?
0.5.
You'd need 2 here, right? It'd be 0.5 plus 2 full intervals would give you the x value that you'd plug into R to get the pretend rate at 5. Does it make sense? Okay, so let's get a general structure for this. So really, this left is really A plus, this is delta x. So what does that number 3 represent?
How many times is delta
Steps.
What is that number?
Oh, I know.
What is it? What's that number 3 represent?
Steps.
Full intervals. How many full intervals from A to that left x value? So this is the number of full intervals. Number of full intervals. So this is the general structure of finding that left x value. It's going to be the starting value A plus the number of whole intervals times delta x. That should make sense. Does that make sense? Okay. So let's try another example. I'm going to change things up here. We'll make A, say, 0.23, and delta x of 0.68. And A, now A is what? What did I say? 0.23. So now A is 0.23 and delta x is? Okay. Find the current left x value. The current value of x left. Go.
Question.
Yeah.
This loop is that A obviously is going to be 0.23
Yep.
I can't tell what the first. I can't tell what the first one is.
Doesn't matter. It starts at 0.23.
30.
Maybe, are you seeing?
Yes, yes,
This is not a dot. There we go. Is that better? There we go. Sorry about that. How about Nishi or Nishai? How'd it go? Give it a shot. So, we're trying to figure out what this x. We're trying to figure out what this x value is right here. What do you think? How would you get it? What is it? Okay, and how did you get that? 14 intervals. Okay. All right, so she took 0.23 plus 14.68. 0.23 plus 14.68. Is that right?
Yes.
And what do you get?
9.75.
So this time we got 0.23 plus 14.68. And that was, what 9.75? Looks about right. Okay, so what is the pretend rate at 10.1? What's the pretend rate at 10.1? 9.75? R of 9.75. What's the pretend rate at 10?
Still R.
R of 9.75, because it's going to be that same constant rate through this current interval. Okay, got the idea? All right, let's try another example. What's our goal? Our goal is accuracy. So let's do
A lot of it.
All right, so do you see how the... Oh, shoot. something different here. Right there. Okay, so first of all, do you see how when delta x is small, do you see how the resulting step function does a really good job trying to pretend to be the actual rate function? So that this is our goal, more accuracy, because we want to get accurate results. So this pretend rate function, if we make delta x small, we get a much better function that's trying to mimic r. Okay? So I got the same starting point. .23. All right. What the heck? Let's do 0.15. There we go. All right. Delta x is, and why are you all sighing? Why? Because you think you have to count, right? So let's use our brain so that we don't have to count. So we need. So what was our general structure here? Our general structure was starting value plus what? Number of whole intervals times delta x. So what's the obstacle here? What is the challenge? Number of whole intervals. So we need a new strategy, because if we want accurate results, we're going to have very small delta x, and we can't sit here and count, right? So we need something mathematical that can get that for us. So we're looking at just this part of it. How are we going to get? We've got x equals 8.53. The current value of x is 8.53. We've got the starting value of a is 0.23. And we got our delta x of 0.15. So somehow with this information, with these three values, we have to come up with a way to generate the number of whole intervals so we don't have to sit here and count like this. Because we don't want to do that. We can't. What if delta x was 0.05 and we're out at 50? Right? So it's very impractical to count, especially if the delta x gets even smaller. So can you figure out a way to generate the number of whole intervals given this information? X is 8.53, A is 0.23, delta x is 0.15. See if you can do it. See if you can figure it out without counting. So use math. Okay, anyone come up with it? Think you got it? Somebody new. Let's see. Yes, sir. How are you going to use these three numbers to come up with this number of whole intervals?
You have
Okay.
Does this replace them in the formula? Or like it's going to be XL minus A over delta X. Which equals
But we don't know what XL is. We're trying to find XL, so we can't. We're trying to come up with a way to know the number of whole intervals so that we can calculate XL. We don't know what XL is.
Oh, I thought XL was equal.
No, that's blue. That's the current value of X. The current value of X, the blue one. That's 8.53. We're trying to find XL for that blue value. Yeah. Okay. All right, so let's start. I'm going to interrupt you. You first said 8.53 minus 0.23? Okay. And what does that represent? So if you take 8.53 and you subtract 0.23, what is that about? What is that? It's what? The whole distance from A to our current value of X. The whole distance. Okay, and then what? And why would you do that? So we're gonna ask how many intervals of width 0.15 fit into that distance, right? So if 8.53 minus 0.23 is that distance, then we're gonna ask how many intervals of 0.15. It's like, remember, quotient, measuring one quantity in the unit of another. So we're measuring that whole distance in this unit. How many of these will make up that whole distance? And what do you get when you do that? What is it? Exactly 55? 55.333. What's the 0.333? 0.322 an interval. That's from XL to our blue value, right? So do we want that? No, what are we going to do? We just want the whole intervals. So how many whole intervals is that? 55. We're just going to chop off the decimal, which is this extra little partial interval, and grab onto the number of whole intervals. So there are 55 here. 55 whole intervals. Does that make sense? So we need a mathematical mechanism that does that, that finds the greatest whole number less than a given number. Okay? And what that's called is the floor function. The floor function, if you apply the floor function to a number, it'll give you the greatest whole number less than a given number. That's exactly what we need, because when we calculate the number of intervals, we're going to get this extra little part of an interval that we don't want. So we're going to chop that off. Even if it was 55.8, we don't want to round up. We want the number of whole intervals. We still want 55. So that's where the floor function comes in. So what it looks like is this. You put brackets with little bar like that. So like that and like that. That's the floor function. And by doing the floor function of this number 55.3, it returns, instead of 55.333, it gives 55. Without the floor function, 55.333. Do the floor function of that number, you get exactly what we want, the whole number of intervals, 55. So then we're going to take 0.23 plus 55.15s. And that gives us, what, 8.48?
Don't make you add the 0.22 afterwards.
No, we want XL. We want XL, right? Our goal is we want the number of whole intervals to get the X value at the left side of the current interval. So we don't want the 0.23. I'm sorry. What were you asking? What were we saying?
Well, I got 55 times 0.15 would be 8.25 plus A would be 8.
Right. That's right. That's right.
Okay.
Yeah. So this overall calculation will be 0.23 plus 55 times 0.15.
Yeah.
And what'd you get?
Yeah.
8.48. So that's the left side of the current interval where X is 8.53. Okay, does it make sense? So now we can write this generically, this XL equals A plus, so how do we get the number of whole intervals? We did the floor function of, what's 8.53? X. What's the 0.23? A minus A over delta X. We want the floor of that. What does that give us? The number of whole intervals times delta X. All right? And we call, so instead of using this, we can actually use function notation, and we'll call the name of the function left. That's our name, so left X. Gives us the X value at the pointer, the X value at the left side of the current interval. Because we're going to take that, what? We're going to take that value and plug it into R to give us the constant rate for that whole interval. Are you following? Does it make sense?
Good question.
Yeah.
So if I were to use the right side, I would just use one more interval instead of the left side of the 10 function, 10 rate would be just one more function or one more interval.
Yeah, so you could, instead of, yeah, you could add one more interval in the formula, and that would get you the right side. That's right. Yeah, so you don't have to start from scratch. You can actually use this one to build right X very easily. Exactly. Okay, so what was left of 8.53? So this is a function now. The name is, this is the name, this is the input, and the output is? Okay, so I want you to talk about the, so this is a true statement, that left of 8.53 is 8.48. So is, say, left of, what, 8.4? What's, or no, sorry, what's left of 8.49? What's left of 8.49? So I want you to answer that question, and then I want you to discuss what is the input into the left function, and what is the output of the left function. What's the input? First answer this. What is left of 8.49? And then generically, what is the input into left? What's the output of left? Go. And find left of 7. And then find left of 7. My pen. Where's my pen? Where's Tammy? Tammy, no. Tammy, what is left of 8.49? It should also be 8.48. Okay. So in general, what is the input into this function now we've created called left x? What is the input into that function? What does it represent? What is the input into left x? So which x value? Where the pointer's pointing at or the blue one? It's the pointer. The input is the pointer x. Is that the input into left x? The pointer x value. No. No, what's the pointer x value? That's what we're trying to find. That's what we're trying to get. That's the result of all this. What's the input into this left function? The current value of x, whatever x is. Okay? Whatever the current value of x is. And I'm showing that with the blue and blue. So that just sweeps through all the intervals. Okay? X just sweeps through all the intervals. Okay? See, watch this value going up. That's what I have for n. Okay? And then given a current value of x, it's going to be in some interval. What's the output left of x then? What's the output? How am I showing the output? No, it's not R. This is the thing that students get really messed up with. Look, left of 8.53 was 8.48. What did that number mean? 8.48. It's not a rate. As many times as you say it, it's still not a rate. What is it?
The value at the left side of the interval, the x value is in.
Right. It's another x value. You put in an x value, the current value of x, whatever it is, this left x function gives you the x value where the pointer is pointing at the left side of the current interval. It does not give you a rate. It gives you another x value. That's what we've been working on the whole time. It's this, right? It's this. You put in, let me make the intervals bigger. What's the input? The input's the current value of x. What's the output of left x? The x value at the left side of the interval. Got to get this. We haven't talked about rate yet.
So it's not actually the output, it's the x.
No, it is output of this function, which is another x value. So this left x value, left of x function takes an x and gives another x.
Oh, we're not talking about R.
Right. We're not talking about R. It's not the rate. It takes x and gives another x. It takes x and gives another x. So it takes the current x value, which could be any x value, and gives the x value at the left side of the current interval. So now, how do we get the rate at 8.53? R of 8.48. How do we get the rate at 8.49? R of 8.48. Anyone find left of 7? So that was with the old delta x. What was it again? 0.15? So what was our left of 7? 6.9. So how do we get R of the pretend rate at 7? R of 6.98. Okay, so isn't that then, if I want the rate, let's see, am I getting, let's look here, okay. So x, 8.53, left x, is it a rate? Is this the rate? No. It's the x value at the left side. So it's a function that outputs another x value. It's a function that outputs another x value, not a y value. And now if we want the rate, what's the rate at x equals, or the, this is the new function we're going to call step. Step is going to be our approximate rate function. It's going to take the current value of x and give the pretend rate. So what is step at 8.53? How are we going to get step at 8.53? What about 8.48? R of 8.48. It's going to be the rate at the left side of the current interval. So we've got this current value of x. We've got its left x value. We want the rate of that.
What was the purpose of step x?
Step x is the pretend rate function. It is the pretend rate function. I just introduced that. This is the new function we're building. And where did the 8.48 come from? What is 8.48? Left of? Not left x. In this case, left what? 8.53. So what happens? Let's track it. A current value of x, 8.53. We put it into left, and it gives us the x value at the left side, 8.48. And we take that, and we put it into the rate function, and it gives us that pretend rate at 8.53.
So, when you found 7, left of 7, what did you use for A and X? Because
Okay, so now let's do 7. She wants to do 7. So if x equals 7, what is left of 7? 6.98. What's the value of the pretend rate at 7? R of 6.98, which we could also write R of left of, not 6.98, 7. Left of 7 will give us the 6.98. R of 6.98 gives us the pretend rate at 7.
how did you get 6.98?
How did you get 6.98?
What values for A and delta X?
The same as before, 0.23 and 0.15. So I didn't change those. Okay, so what are we seeing here? If you want step, I'm going to erase all this. Can I erase all this? So we started with what? 8.53, and then we did 7, and we did left of x. And we got 8.48 and 6.98. Is that right?
I'm getting 7, I'm not getting 6.98.
You're not getting, is 6.98 right?
Right.
Yeah, question.
Because you're supposed to use only 45, not that.
You have to have the whole number of intervals. The whole number of intervals to get to the left side.
If you plug in it all at once, it'll give you 7. You don't just use X7.
Remember, you had the whole number of intervals, not that ending partial interval. So then step of x is going to be R of 8.48, which came from R of left of 8.53. R of 7. So what is step here? It's going to be R of 6.98, which came from R of left of 7. So what is our step function then? So this step x, if it's 8.53, we do R of left of 8.53. It gives us the approximate or pretend rate at 8.53. If it's 7, we do R of left of 7. Because that left of 7 will give us the left x value. We take that left x value, plug it into the rate. It'll give us the right rate. So how can we summarize step x? Where does step x come from? It's R of left of x. You take the current x, you map it to the x at the left side, you take that left side x and you put it into the rate function and it gives you the approximate rate in that for that value of x. Okay, anybody have a question? The key here is the output of left x. Is it an x value or a rate? It's another x value. It's the x value at the left side of the current interval. So even though we're used to output being y, this left x function has an input of a current x and an output of another x, the x at the left side. And then we take that x at the left side and we plug it into the rate, and it gives us that value of that constant rate in that interval. Okay, anybody have a question? So let's get out graphing calculator and let's give this a shot. Okay, so I've got text in between these command lines. You don't have to put the text in, but the text is giving you the instructions for what each command line is. So let me make it a little smaller. Hold on. Okay, just don't do 4. 4 is optional. Just skip over 4 for time's sake, okay? So we're going to do a rate function. Define your rate function as e to the cosine x. And then we're going to define, two things on the same line. We're going to define the rate function and our starting value a of 1 for the accumulation. Okay, so you've got some work to do. So the first line after that, after you define the rate function, is to graph the rate function. And graph it for all x values starting from a and greater than a. This has done this a lot, so you should know what you're doing by now. So starting at a, you're going to graph the rate function for values of x greater than or equal to a. All right, and then we're going to assign delta x. We're going to assign it to be 2. Remember, we could call this tree. We could call this hat. Graphing calculator does not know what we mean when we choose delta x. That's for us. That's for us, right? It doesn't know that a is the starting point. That's what we call it. It doesn't know that delta x is the width of an interval. It's just a variable to GC. But it helps us. Okay, it helps us. So remember on the map, option J for symbol delta, For PC, just use something else. Delta X or del X, something else on a PC. All right? Don't do number 4. In fact, let's just get rid of number 4.
Okay.
Just optional, and I don't want to spend the time on it. Okay, step 5. Define the function left. Okay? So remember, you want that whole string to be a single label, and that's going to be the name of your function, like F, or like R, like capital R. So you left instead. You're going to define that function left. Okay? And that's what we worked hard in class today to do. And then after that, you're going to define the function step. Again, that whole word step is like capital R, or like left. It's the name of the function. So let's see how we do on this, okay? So this is your these are your tasks. Could I get this to work before we leave class? Question. Oh, sorry. To get the for function, you just type FLOOR, and the brackets pop up. You got it. Yes.
And then times. So like those are all the but don't type 2, type delta. Oh, just yeah. Plus, no, outside. Left of X, yes.
This one, yes. Yeah. You did time, so that's not the point. You did do the full 9 on step. Yeah. Yeah?
Is it step R?
Yeah, but you didn't graph it. You defined it, but you didn't graph step. So yeah, you defined left and you defined step. This should be step of X. But then you didn't, so we didn't graph it.
So we have everything.
Y equal to What is that? That's so cool. Here, professor, so professor, is that what we should see? What's cool?
Yeah. Yeah. For now, that's right. For now, that's right.
Can you set it to choose
Okay, how do we get the step X function? We want the rate where? At the left side of the current interval. That's going to give us step. We want the rate. And how do we get the rate at the left side of the current interval? What are we going to put into the rate? Left X. The output of left X is the X value at the left side of the interval. We're going to find the rate at that value. And then we're going to graph step. How do we graph? Y equals. Or X greater than or equal to A. And you should have gotten something like that. I'll do blue. Okay, is this what we wanted? Is this what what we were envisioning for step when it came out? No. What's different about this? We were just envisioning what?
delta X.
What's different about this versus what we were envisioning?
Delta Y is delta.
So these vertical lines, like what are those about? Because we just wanted these constant rates of change that we're getting from the rate function. So what does graphic calculator, how does graphic calculator produce a graph? It doesn't know what step X is, it's just doing what we said. And how does it graph a graph? Well, it takes just a finite number of X values and calculates the corresponding Y values and then does what? So it finds a bunch of points and it does what? Connects the dots. It connects the dots. So what is it doing? It's finding this point here and this point here, and it's connecting the dots between every point that it finds. So we don't want those vertical lines. So here's what we do. We want it to graph everywhere except at the endpoints of the intervals. So we want to graph Y equals step X if X, okay, so option equals is not equal to. We don't want X to be equal to the end of an interval. So how can we talk about the end of every interval? What's the end of every interval? Left X, right? That's the ends of the interval. So if we graph it everywhere except at the X values that are the left ends, that should get rid of our vertical lines.
How do you get that equal sign?
So max option equal. Does anyone know how to get not equal on a PC? Look on Blackboard on that list of that's keyboard shortcuts. Control Shift what? Control Shift A, N. Control Shift N on a PC gives you the not equal. Control-Shift-N. Now here's the beauty of this. Just let me show you one more thing. This is super cool. Watch. So if I can take delta x now and make it 0.2,
It's going to be dynamic.
everything changes automatically. I can take delta x and make it 0.02. Now watch this. I'm going to turn off the original rate graph. I turned off the rate graph. What are you looking at here? Is this the actual rate function? I turned off the rate function. This is for x. Let me make it a little bit bigger.
It's too tough.
Here's delta x of 0.12. Is it doing a good job of pretending to be the actual rate function? Yeah, the smaller I make this. So this is another. These are constant rates. These are constant rates on very small intervals that does a really good job of replicating that rate function. Okay, homework and quiz on Thursday.